So what do we know from the problem? The radius, okay? And what's the radius? 28 centimeters. Okay, what else do you know? Okay. 100 centimeters per second. Is that the only... Yes, so speed or velocity, so... Alright.
Why wouldn't it be angular velocity?
Why wouldn't it be angular velocity? Because centimeters per second or meters per second is a standard velocity, whereas angular would be radians per second. Okay. Someone said acceleration? Alright, and I would say there's probably one more... Okay, so it's rotating with that constant acceleration, but more important, the rest starting at rest, to your initial velocity of 0. And then what are we solving for? Coefficient of friction, mu. So next up will be to start to develop an equation. So let's start with what we know. If we want mu, what is the formula that has mu in it?
Wasn't it normal force?
Okay. So the frictional force is equal to the normal force times mu. Okay. Or we could rework that and say the frictional force divided by our normal force is mu, right? Since we're going to get mu by itself. So ultimately, this is the formula that we want to use, is friction divided by the normal is equal to our mu. If we this is what we have. We have a spinning wheel. We have our little candy on it. Yeah. So as it's spinning, that normal force is acting in what direction? So where's the surface at? Surface is below it, so it's perpendicular, it's going up. Okay. So this would be our normal force. What other forces can we say? Gravity. Going down. Yeah. So it says in the problem we've got friction happening, right? So where do we think that friction is going to come into play?
Going towards centripetal, right?
Okay, so that friction is going to be what acts as the centripetal force. It's what's holding it inward to keep it from flying out. So without friction, you'd go flying off with your tangential velocity in that straight line. So I have to have enough friction to keep me on that track. So my frictional force will act as my centripetal force. So if friction is acting as the centripetal force, how do we find centripetal force?
NVR squared.
V squared over R. Okay. And then looking at our normal force is in line with our gravity. We don't have any other forces in that up or downward angle, so that means that our normal force is going to be equal to our gravitational force, right? Equal but opposite. One down, one up. Okay. So this is what we need to be able to plug into our problem. So where I have friction, I can use this equation in place. Where I have normal force, I can use this equation in place. So what would my new equation look like?
V squared.
Okay.
Over R times mg.
Okay. mv squared over r. Now am I multiplying by mg? Okay, I'm dividing by mg, so that mg would be on bottom. Okay. So it would stay on bottom. If that's uncomfortable for you, you can keep the n over where it was. And so because you have numbers, if it's uncomfortable to have fractions on tops of fractions, then treat it as we had at the beginning, and you can plug in your numbers, get a single value, and then solve from there. Okay, do what works for you. Yeah, so for some of you, this is more comfortable than having a fraction on top of a fraction. Okay, part of that comes from how much math practice you've had, maybe what kind of calculator you've got, that kind of thing. But we have values here. So we have a velocity, we have that acceleration from gravity, we have a radius, okay? They did not give us mass in our problem, correct?
Yeah.
So what do we need to recognize there?
There's no change.
Yeah, don't they cancel if they're both?
Okay, so they do cancel out. So I got a mass here and a mass here. I got a mass on both sides. Or if you have a fraction on top of a fraction, So if you are someone who's working with that fraction on top of a fraction, I'd be dividing by that mg, so it'd be down here on the bottom, and it'd be mass over mass, or 2 over 2 takes us back to 1. So you have mass on both sides, it just cancels out. This one goes away, that one goes away, don't need it. So that becomes your math problem that you solve. Go ahead and take a second, try it out. So again, algebraically, that would be the same as... So fraction-wise, it looks something like that, if you're working off of the old method. That's a good question. Since they are all in centimeters, you can leave it and it's going to cancel itself out. If you want to convert it for just that practice and making sure that everything's there, that's fine. But because they're all in centimeters, it's not required to convert. So common terms or consistency is what I always go back to. So we're coming up with 0.364. And since mu is just a ratio, it has no units to put in. Essentially, we have 2 discs that we're going through. 99 centimeters apart. And they're spinning on this wheel, this axle. So they spin for that angle of 21.9. And since they're both connected to each other, they'd have the same angle, they'd go the same speed, all that other kind of stuff. So our first one we'd hit, and it's spinning, so like it would have hit here down at the lower section, and then as it spins, now that dot's going to rotate up. My bullet's going to still be going along a straight trajectory, right? So now it's going to hit this one at what its horizontal would be. So by knowing how far the difference from this point to this point in terms of that angle, that's how we're able to figure out how fast something's going. Because we can tell the difference between the first spot that it hit on this one, and then, so it fires, it hits here, and then rotates up, and while that bullet keeps going, now it's going to hit this one, and hit the next one, the next one, the next one, the next one, the next one. So it's that idea of when you want to drop something, you're dropping before you get there, so as it fires, it's that other disc is still going to be moving as it makes that distance. So if I can figure out how far the distance that this is traveled, okay, and those times, then I can start to figure out how fast it's going. What do you know?
Oh, so it's spinning.
Okay, so we have angular velocity.
Wasn't that the fish?
Okay, so the fish is per minute squared or per second squared, so if it's just revolutions per minute, that's going to go towards our angular velocity. So acceleration always has that square factor. And then 21 degrees will be our theta. Now both of these need to be converted. Okay. So if I go from 516 revolutions per minute.
Is it pi or 2 pi?
Okay, 2 pi, so 1 revolution is 2 pi. Okay, so that's going to get me to the radians that I want. And then minutes versus seconds.
60.
Okay. 1 minute is 60 seconds. Okay. So I'm going to do 516 times 2 pi. That's going to get me my radians. And then divide it by 60 seconds. That's going to get me my radians. So that'll give me an answer in radians per second, which is what we want our angular velocity to be in. So 54.035, and that's going to be rads per second or radians per second. By that same measure, we need to take 21.9 degrees and convert it into radians as well so that we have common terms. This is one of those where it's a standard formula on your formula chart. So right up on the very top left corner underneath the triangle, it tells you how to go from degrees to radians. So it says on your chart that degrees times pi divided by 180 will give you radians. So 21.9 degrees equals how many radians? So we're getting 0.382 radians for our theta. Okay. So we have a W and we have the radians. From that, what could we find? And the other question is, what are we trying to find?
Try to find velocity.
Trying to find velocity. And what's our standard unit equation for velocity? Okay, meters per second, right? So if we have meters per second, we need some amount of distance, and we need some amount of time. Okay. Do we have a distance up there?
Yes.
So I know that it's going to go 99 centimeters, or 0.99 meters. Since we didn't convert the last one, we'll go ahead and convert this one for that practice. So 0.99 meters, but do we have a time? No. Can I get time from these other two values that I have? Okay, what is the equation that will relate that omega, our radians per second, to our theta, our radians? So if our omega is 54.5 and our theta is 0.38, then we can find our time. And once I have that time, I'll be able to come plug it in over here to get my velocity. All right, teeny tiny number, right? So how many zeros? 0.00. And then what? 7. Like that? Okay. So that's our time. Now we can come and plug it in here and get that velocity. Now I would just carry that in. So 0.99 divided by the answer, because if it's that small of a time, you probably want every possible decimal point. So do 0.99 divided by and then second answer. Okay, so you're able to carry it through. The blue calculators have that same answer function on there. So if you do the second button and the little negative button down in the bottom corner, it brings up your answer, right? So 140. And since we converted that 0.99 to meters, this would be meters per second.